Right, my starting slide for this evening is our current image of the year. It's a magnificent solar prominence imaged in hydrogen alpha by Rob Parsons. And we saw a bit of this afternoon. It was about 10 minutes before the event was due to finish, but more about that later. Good evening, everyone. A very warm welcome to the Astronomical Society of Edinburgh's online meeting for April. I'm Neil Martin, current president of the Society. And for those joining us on Zoom, please can you ensure that your microphone is muted? Thank you very much. We have two items on our agenda this evening. In a moment, I'll formally introduce our guest speaker for this evening, Anwesha Sahu. And following Anwesha's presentation and the Q&A, I'll close the session with a look ahead to what we have coming up over the next few months. So without further ado, let's begin. Anwesha Sahu is a PhD researcher at the University of Warwick, working on accretion and outflows in extreme astrophysical environments. Anwesha completed a BSc and Master of Science at the University of Birmingham in 2023, and her dissertation covered machine learning techniques for radio astronomy. During her time in Birmingham, Anwesha was chair and outreach officer for the University of Birmingham's Astronomical Society. And as we were getting set up, Anwesha said that she has a soft spot for astronomical societies. So it's fantastic to welcome her this evening. So let's give Anwesha an enjoyable evening. Outside research, she can often be found working on science outreach projects and cites orbits as a personal favourite. And if she's not talking about astronomy, she will likely be talking about guinea pigs instead. So maybe there's a segue into another presentation in the future. But tonight, Anwesha will be definitely talking about astronomy and white dwarf pulsars in particular. So, ladies and gentlemen, please pop yourselves off mute for a moment to give a very warm ASC welcome to Anwesha Sahu. And Anwesha, I will hand it over to you.
Thank you very, very much for the warm welcome. I'll just start sharing my screen. I think you might have to turn off your screen share for me to be able to share it.
Which is up here. There we go. There we are.
This should just take a second. Let's see, hopefully the full screen works. Are you able to see it in full screen? Fantastic.
Yeah, that's perfect. Yeah.
Great, thank you. Well, it's really nice to be here to talk to you, everyone, this evening about white dwarf pulsars and about my research. Thank you so much for the warm introduction as well, and it's a great joy to be able to talk about some of the things that I love most, especially on a Friday evening, because this is a lovely way to end the week. So yeah, as the title slide says, today I'm going to be talking about white dwarf pulsars. And this might be a relatively novel term for many of us today, and that's because it is a relatively novel object. It's only the first one, white dwarf pulsar, was only discovered in 2016, and we have less than 5 systems confirmed to date. So it's really exciting new research that we're doing at Warwick. So before I get started about the nitty-gritty details of the science, I thought I'd introduce myself a bit more and my research and non-research interests. I'm, as introduced previously, I'm a PhD researcher at the University of Warwick, and my PhD specializes in accretion physics. Within the wide topic of accretion physics, I focus primarily in the radio astronomy side of things. So I identify as a radio astronomer. So that means that I get to work with non-typical telescopes. So I work with radio telescopes, which, as the name suggests, they observe the universe, they study the universe in radio wavelengths, so much longer wavelengths than optical wavelengths. My preferred telescope, which I use for all my research, is the VLA. That's the Very Large Array, the Carl J. Jansky Very Large Array telescope in New Mexico in the States. And that's a radio telescope array that comprises of 27 radio dishes. Each dish is, I think it's either 30 or 60 meters across. And There's 27 of them, and the longest baseline, meaning the longest distance between any two telescopes, that can be up to 31 kilometers, which means that we get fantastic resolution. The longer the distance between each dish, the higher the resolution. And this image that you see down here, can you see my cursor where I'm moving it? I'm moving it around the Meerkat GPS image. Okay. I'm going to assume you can't see it, so I'll just describe where the image is. So if you take a look at the image that I have in the lower panel that says Meerkat GPS MW radio galactic plane, that is the image of the Milky Way galactic core taken in radio wavelengths. And because of radio telescopes' interferometry capabilities, because you have multiple dishes, the resolution that we get is unparalleled. And that's why we see structures in this image that we cannot see in optical wavelengths. We see these filament like things, so you might see little long wispy thread like structures emanating from the center of the galaxy there. We don't see that in the optical, and also we have no clue what that structure is or what those structures are. So that's an active area of research. And I'd like to think of radio astronomy as astronomers having a pair of supervision goggles, because you get to see the universe with a whole new set of perspectives. So other than radio astronomy, I do work on transient classification and just transient astronomy. What that means is any powerful phenomenon in the universe that is short-lived, in the sense that it would have a brightness change, so it would be bright for a short period of time, and that would be symbolic of a really powerful process that is powering that brightness change. So that's the field of transient astronomy. And for that, Warwick primarily utilizes the GO2 telescope, which is the gravitational wave optical transient observer. And these telescopes are located in Spain and in Australia. And yeah, they scan the night sky once every 3 to 4 nights. And they essentially compare the images to see, has anything changed in brightness? So that's one of the collaborations I'm involved with. Other than that, you'll find me adoring my guinea pigs. If I'm not talking about astronomy or reading, I absolutely love reading, and I love outreach activities. So yeah, that's one of the nicest parts about being a researcher in the 21st century, is that nowadays most research institutes really encourage work-life balance, and it's something that we're all aspiring towards. So yeah, with that, I'm going to move on to the outline of today's talk. So today we're going to talk about white dwarf pulsars. So before we can appreciate what white dwarf pulsars are and how we get to white dwarf pulsars, we're going to take a look at the ingredients for a white dwarf pulsar. As the name suggests, that involves a white dwarf. So we're going to first look at how we get to a white dwarf star. Given that this is an astronomy society, I presume many people in the audience are familiar with the life cycle of a star, so I will do my best to condense this section as much as I can. And secondly, we'll look at what is a pulsar, how does it form, and finally, we'll take a look at what white dwarf pulsars are, what formation scenarios we have for them, which will then lead us to a case study where we'll focus on ARSCO, which was the first white dwarf pulsar ever discovered. My allergies might act up, so please excuse me if I sneeze or cough. Sorry, just felt a sneeze coming on there. Right. Yeah, so we're going to look at ARSCO, which was the first white dwarf pulsar that was ever discovered. And finally, we'll look at prospects. Do we see more white dwarf pulsars on the horizon, and where we can take the physics of white dwarf pulsars from there? Right. So at the core of astrophysical processes is fusion, the process of nuclear fusion, because that's what powers stars, such as our sun. And to get to the stage of forming a star, like the sun, we first start with something known as a protoplanetary disk. What this is essentially a huge mass of gas and dust that has somehow been nudged through a shock wave or disturbances in the local region to start coalescing and rotating. Eventually, as this huge mass of gas and dust coalesces, it will result in a really hot and dense core. By the time that the core gets to temperatures and pressures high enough to sustain the fusion of hydrogen, that's when you get a protostar, and vast amounts of energy are released in the process. So, the key chemical process that occurs here is the fusion of hydrogen into helium, and that releases a neutron in the process, which then contributes to the energy needed to trigger further fusion, further atoms fusing together. So once you get to a protostar and you have hydrogen fusing into helium constantly, you then have a young star. If this ball of hot gas and dust starts off with an initial mass of less than 10 solar masses, then that will result in a star much like the sun. So that's your average yellow star that we see. So for a star that is about the mass of the sun or less than 10 solar masses, as that star evolves, it's going to continue fusing hydrogen into helium throughout the course of its life. And that main sequence stage where it's fusing hydrogen into helium will last a very long time, billions of years, as we can see from our sun. But by the time it gets to the stage where it's mostly helium, the core will begin to collapse because you'll start getting the heavier elements collecting within that very core. So the core begins collapsing and heating up to higher temperatures, and the outer layers start puffing up because you've got helium building up in those outer layers. And the heat and the light contribute to this puffiness. In the case of our solar system, by the time the sun puffs up and becomes a red giant, it's likely that it will have expanded large enough to engulf the orbit of Venus, and it might be even approaching the orbit of Earth. So we're looking at really large scale expansion in this case. So when the star is at the stage where it's a red giant, you no longer have hydrogen fusing into helium as the dominant process. Rather, the process that dominates at this stage is helium fusing to form carbon and oxygen. As you can tell, carbon and oxygen are going to be much heavier or much more massive elements than hydrogen and helium. So, what this will result in is that it's going to contribute to the core becoming even denser. What we then see is that the outer layers, when the core is unable to sustain the collapse anymore, the outer layers will then start shedding. And that very process is what results in beautiful planetary nebula that we see. And these are some of the most favorite astrophotography targets, and some of them, and we do have quite a few visible, very beautiful and beautifully and clearly within our local stellar neighborhood. And they are the results of red giants or main sequence stars like the sun. For me, the most exciting part is what's left behind in the center of these planetary nebulae. What we have in the center of every planetary nebula that we see is a white dwarf star. And that white dwarf star is the remnant core of the red giant star. That's the core that's left behind that has essentially stopped collapsing due to a quantum mechanical force or feature called electron degeneracy pressure. And by this stage, you will get some minor fusion of carbon and oxygen to form some trace elements, but still predominantly the core will be carbon and oxygen. And yeah, this slide is just reiterating what we had in the previous slide. So you're left with a planetary nebula with a white dwarf star in the core. To give you an idea of the sizes of white dwarf stars, we're essentially looking at the entire mass of the sun, or most of the mass of the sun, essentially, condensed condensed or collapsed into a size that is not that much bigger than the Earth. And this means that white dwarf stars are extremely dense systems. And that's also due to the fact that it's held together by electron degeneracy pressure that it's able to sustain these really high densities. And we see white dwarf stars everywhere around the universe. That's because stars like the sun are the most abundant stars that we see in the known galaxy. So now that we know how a single white dwarf star forms, we can take a look at how binary white dwarf stars form, because this is where the physics starts to get really interesting. So step one would be to get to a stage where we have two stars, just any two stars, rather than just getting to a white dwarf. So the first stage to get a binary star, it essentially requires you want to have two stars within the protoplanetary disk. So far we don't really have concrete evidence saying that one method is definitely the correct method that accounts for all binary star formations, but we have models that seem to explain quite a lot of the observations that we have of binary stars. One of the models that we have so far talks about disk fragmentation, which is essentially where you have a star that's a protostar that's forming within a protoplanetary accretion disk, but due to instabilities in the disk, instead of getting just one star forming, you end up getting two stars within the central region. Alternatively, you could have a region of instability slightly further out from the center of the disk itself, and you would get a second region of coalescing matter, and that will result in two stars that form, one in the center and one slightly offset from the center at an outer location of the disk. So the image on the left here, that is a simulation image of what a protoplanetary disk with two stars might look like. And on the right here, we have a radio image taken with the ALMA array of a protoplanetary disk with two stars. So if you look very closely in the center of the right image, you will see that in the center there is a star, a very bright star, and then around the 2 o'clock position or 1 o'clock position to that central star, there's another bright dot. And that bright dot is a second star that's forming within this system. So we see evidence of binary star formation quite quite clearly in these protoplanetary disks. So here we've now got two protostars and they're orbiting each other. So in a protoplanetary disk where we have two stars, it's almost inevitable that both the stars will have different masses. This will mean that they're going to evolve at different rates because it's the mass of the star, the mass of the core, that determines how fast the star will burn through its fuel. The branch that we're looking at here is the upper branch of this stellar evolution diagram. So we're looking at low to medium mass stars because they are the ones that will lead to white dwarfs. So in this binary star system, the star that is more massive will evolve a bit faster, meaning that it will go through the processes of hydrogen fusing into helium, into becoming a helium-dominated star that's now fusing into carbon, and that's fusing helium into carbon and oxygen sooner. But as it does so, as the more massive star does so, it will puff up. And in that process, it is very likely that instead of the star just puffing up on its own, it will actually have its outer layers being affected by the gravity of that second star. So, more often than not, what we see in these binary systems where one star is more massive than the other and evolving faster, the matter from that second star's atmosphere will actually engulf the second star itself, the less massive star. And when we see that, we call that a common envelope event. So when I say when we see that, we don't really see it with our telescopes directly because we don't really have the resolution to resolve these systems where we can see both stars clearly. We find these out through spectroscopy. So if we put a spectrograph in our telescope and then point the telescope towards the system, we will often see signatures of two stars in it, and that's how we know that it's a common envelope star. So in this case, because the first star has evolved faster and is approaching the red giant phase, it's going to become a white dwarf much sooner. But while this is happening, the second, less massive star is not yet a white dwarf. It is still a main sequence star that has got some matter from the leftover atmosphere of that more massive star still left in it. So at this stage, we've got one white dwarf star and one main sequence star that is still evolving further. But eventually, if you give it enough time, then both the stars will get to the stage where you have two white dwarfs orbiting each other. When we refer to the term white dwarf binary within the astronomy community, what we mean is that at least one star in the system is a white dwarf. There are many cases where we have double white dwarf binaries and we get amazing physics within these systems as well. So my current project, which I'm actually in the process of wrapping up, that looks at binary systems which have two white dwarf stars which go around each other. But that's not going to be the focus of the talk today. I'm just going on a little bit of a rabbit trail. But it's it's very interesting to have two white dwarf stars which evolve into each other, which evolve to orbit each other, because you can then see some really interesting orbital dynamics. So there are these systems known as AMCVNs. AMCVNs are white dwarf binaries where you have one white dwarf and a second star, which is either a white dwarf or a helium star, where they have orbital periods of 5 to 60 minutes or 5 to 65-ish minutes. So they're really rapid orbiting systems. So if you have a white dwarf binary, then you're looking at some lower range orbital periods. But if you have a white dwarf star and a main sequence donor or a low mass main sequence donor, then you can often get something known as a cataclysmic variable star, or a CV, which I think many people or some people in the audience might be aware of, because CVs show some very interesting optical behavior. So CVs, where you have a more massive white dwarf star, that will draw matter or accrete matter from the donor star, which is a low mass main sequence star, and you can see changes in brightness within the system every now and then as it increases larger and larger amounts of matter that then undergo different levels of thermonuclear runaway. So that's white dwarf stars and how they evolve in a nutshell. So now we know how we can arrive at a white dwarf binary. So that covers the white dwarf side of the story for white dwarf pulsars. Now let's take a look at neutron stars. So neutron stars form, or they start forming, pretty similar to white dwarf stars themselves. So you start off with the protoplanetary disk, you get hydrogen fusing into helium and a neutron, but the key bit here is that the initial mass of that cloud of gas and dust that coalesce to form that protostar is not less than 10 solar masses, but is rather greater than 8 solar masses. More often than not, it's greater than 10 solar masses. And when that happens, all the fusion processes that we see in stars, they kind of proceed through in a fast forward fashion. So you go from hydrogen to helium, and then helium fusing into carbon, neon, oxygen, and then oxygen fusing into silicon. But by the time you get iron forming in the core, fusion can no longer proceed, because in order for fusion to continue, the process needs to release more energy than it takes in. But by the time you get iron in the core, to fuse iron, more energy needs to be supplied into that chemical reaction than is produced by the acts of fusion of the other elements. So by the time it gets to iron dominating the core becomes extremely unstable. The core becomes very dense. Neutrons get in the nucleus of the atoms get squeezed really tightly, and that means that the main force that is supporting against the gravitational collapse of that very core is, instead of electron degeneracy pressure, now it's neutron degeneracy pressure. So by the time the core reaches a mass of 1 to 2 times the mass of the sun, even that pressure isn't enough to stop the star collapsing, and you then end up with a supernova. And supernovae are some of the most beautiful processes that you can see, or events you can see in the universe, unless you happen to be involved in one. So this image that we see here is of the Crab Nebula. And these are fantastic imaging targets, spectroscopy targets, photometry targets, and radio astronomy targets as well, because they often have neutron stars located in the center. So if the remnants of the core of that star after the supernova explosion is less than 3 times the mass of the sun, you're left with a neutron star. If it's much higher than that, then you're often left with a black hole. But let's take a look slightly closer at neutron stars. So when we say the term pulsar, which was originally coined to explain pulsating radio stars, this refers to neutron star pulsars. So for the Crab Nebula, we have a neutron star pulsar, or a pulsar, in the center of this debris field that we see. The image on the right here shows a multi-wavelength image of the Crab Nebula pulsar. So we've got optical data in red and X-ray data in blue. So one of the liberties that we astronomers take to make our images pretty is we can choose the colors that we use to depict different wavelengths, and that gives us beautiful high contrast images. So here in the center, the red dot that you see, that is the pulsar. And the blue lines are the X-rays emitted from this system. So in pulsars, the physics that we see that dominates the radio pulses and the optical pulses that we see from these systems, that's the rapidly spinning neutron star. And the reason we see these pulses very, very regularly, that's because the orbital period, the rotation period of these systems are very regular, and the rotation axis and the magnetic axes, they're misaligned. As a result of that, if the beam of radiation of radio waves or emission intersects with Earth's line of sight once every rotation, we get a single pulse. If it intersects with Earth's line of sight twice every rotation, we get 2 pulses. Now we're going to compare neutron stars and white dwarf pulsars. So I haven't told you much about white dwarf pulsars, and that is on purpose, so we're going to get to that in just a second. So neutron stars, as we've just seen, they result from the evolution of supermassive stars, and they're quite rare. They're much more compact than white dwarf stars. So whereas in white dwarf stars, we're looking at radii large, just comparable radii to Earth, in neutron stars, we're looking at a radius that's comparable to the radius of a really large town. And the mass of a neutron star is 1.4 solar masses, so that's the remnant core of that supernova, condensed into an area that's just about 10 or a sphere that's about 10 kilometers from core to the outer edge. And the magnetic fields are quite strong. However, in white dwarf pulsars, we arrive at these systems through from the evolution of lower mass stars. So we're looking at white dwarfs. The 2 types of stars we're looking at between neutron stars and white dwarf pulsars are completely different. The reason why the name white dwarf pulsar has struck is because we see pulsating radiation from them. But as we're going to see in a couple of slides, we saw that it wasn't neutron stars, but it was white dwarfs that are producing this. So the name stuck, and they're now called white dwarf pulsars, but white dwarf pulsars do not have neutron stars in them. And because white dwarf stars are abundant, we expect to find quite a lot more of them. White dwarf pulsars, white dwarf stars, they have radii 10,000 kilometers, masses about the same as the sun, and much weaker magnetic fields than neutron stars. The most important takeaway from this slide is that white dwarf pulsars are only found in binary systems, meaning you need a white dwarf star and you need something else to form a white dwarf pulsar. Whereas neutron stars, they exist as sole systems, as single star systems. So white dwarf pulsars are not really pulsars at all in the traditional sense. The mechanism is completely different, but they do emit pulsating radiation, hence white dwarf pulsar. So we're going to look at the first white dwarf pulsar that was ever discovered, AR-SCO. So the story of the discovery of AR-SCO is actually quite interesting, because rather than being discovered through some really complex research campaign led by a research team at a university, it was actually discovered by amateur astronomers. And they were observing a bunch of variable stars, and they obtained this light curve. Not this light curve that you see on the screen, but they obtained a light curve of the system called AR-SCO. But they noticed that there was additional scatter and noise, and that didn't seem to fit in with typical observations of variable stars. So they contacted a professor at the University of Warwick. His name is Professor Boris Skansike, and Boris took a look at that and realized that, okay, this system is indeed doing something really strange. So, together with Tom Marsh, who was the founder of the astronomy group at Warwick, um, they uh, they got together a team from our university, and they obtained a more detailed light curve using one of the research survey sky surveys that we have. So this is obtained from the Catalina Sky Survey, and they observed that there's a very regular light curve from this variable star system, AR-SCO, and it shows modulations in its brightness every 3.56 hours. But the light curve seems a little bit messy. There's additional scatter. It's not as neat and clean as you might expect. And when they zoomed in into this noise, they saw that it's not actually noise, but rather it's micro fluctuations in the brightness. So we're not only seeing this modulation in the 3.5 hour period as we saw in this slide, but we also see pulses being emitted every 2 minutes. And those short lived pulses, the 2 minute pulses, result in the scatter. With the image on the right here, what we're seeing is that same scatter, but in different wavelengths as well. So what we like to do in astronomy when we just get photometry data, so that's just looking at how much light a system emits, we want to know what type of light it is. We want to know what elements might be contributing to it, so we can then untangle what type of star it is. So the team went on to get a spectrum of AR-SCO, and they got a beautiful high resolution spectrum, and they saw that it was not one star, but it was two stars. So it is what you might expect from a variable star, but this is where it got really interesting. So there's a component from a blue star, and there's a component from a red star. So it's confirmed at this point that that this binary AR-SCO has two stars, and the blue part of the spectrum is the contribution from a white dwarf star, and the red part of the spectrum is a contribution from an M dwarf star. So it seems to be that we've got regular pulses in multiple wavelengths from a white dwarf M dwarf binary, and it seems to mimic what a pulsar might do. And this was the first that this behavior had been observed coming from a white dwarf binary. It's never really been seen before. And it was visible, this modulation behavior was visible not only in the optical part of the spectrum, in the optical light curve, but also in ultraviolet, infrared, and radio. And luckily, they were able to run a multi-wavelength campaign such that they were able to get observations of AR-SCO in UV, infrared, and radio all at the same time, which is very difficult to coordinate because it takes months of writing proposals and figuring out and organizing that the telescopes are pointing at the same place at the same time, because the telescopes could be located all over the world or even in space. So after a a very determined effort to get multi-wavelength observations at the same time, lo and behold, we see these pulsations across all wavelengths. So now that we've got the spectral data and we've got multi-wavelength data, we can finally start to untangle what is going on in this system that's causing it to mimic what a pulsar might do, but without a neutron star. And the leading model that we were able to come up with, after confirming that it is indeed a white dwarf star and a red dwarf star, is that it seems that AR-SCO, the first white dwarf pulsar, has a rapidly spinning, highly magnetic white dwarf that is leading the energetics of the system. In addition to that, there's a second magnetic M dwarf star, or a red dwarf star. And anything that's magnetic, much like all the magnets that we see on Earth and the Earth itself, magnetic things have magnetic field lines. And that can be applied to this binary as well, where the magnetic field lines of the white dwarf and the red dwarf intersect, electrons are accelerated. And this leads to the radio emission that we see from AR-SCO. So where you have a charged particle going through a magnetic field, you get radiation. And that physics is occurring, that very physics that we see on Earth that allows us to communicate using our phones is what's happening in this very far away system. Some key facts about AR-SCO are that it has an orbital period of 3.6 hours and a spin period of about 2 minutes. Coalescing this model of a rapidly spinning magnetic white dwarf and a magnetic M dwarf with the observed properties of AR-SCO having a 3.6-hour orbital period and 2-minute spin period is quite a bit of it's quite a brain exercise, because it's not something that we still agree on in the field either. So isolated white dwarfs, they typically have a spin period of about 1 day. So these are white dwarfs that don't have a binary companion. And accreting white dwarfs like cataclysmic variables of CVs, they have spin periods of hours or minutes. The key difference between isolated white dwarfs and cataclysmic variables is that cataclysmic variables, or CVs, they are actively accreting matter. So you have the white dwarf that's accreting matter from the donor star, and that's what's caused it to spin up. So it's got a spin period of hours, whereas a lonesome white dwarf will only have a spin period of about a day. In AR-SCO, we observe an orbital period of about 3.6 hours, but it's not undergoing accretion. So AR-SCO is a white dwarf binary system that is not undergoing accretion, but has an orbital period that is fast enough to place it within the category of accreting white dwarfs. And the reason why accreting white dwarfs have a spin period that is much lower is because as the matter from the donor star impacts the accreting star, so the more massive star in the middle, it transfers its momentum to the central star and gives it that little push. A nice analogy would be to think of in a playground, if you think of a merry-go-round, and you have someone, let's say you're spinning on a merry-go-round, and there's someone with a water gun, a really powerful water gun, just continuously spraying the merry-go-round with water in the same direction that the merry-go-round is spinning. That will result in the rate of rotation spinning up rapidly, and that's what we see in accreting white dwarfs. But AR-SCO shows no evidence of accretion in its spectrum. That just raises further questions. Additionally, it is highly magnetic, meaning that accretion is going to be inhibited. So in white dwarf binaries, where we have really strong magnetic fields, in cataclysmic variables, for instance, that suppresses accretion because you no longer get an accretion disk. If there's any sort of mass transfer that's going to occur along the magnetic field lines and directly onto the poles, but this will be a much smaller rate of mass transfer as compared to a mass transfer with an accretion disk. So even if AR-SCO had some accretion going on in the past, if it's been this magnetic, that will not account for the timescales that we observe it to have. So how can it spin so fast and be magnetic? Now, it's very likely the AR perhaps wasn't born magnetic, it became magnetic as it evolved. And this leads to one of the proposed formation models. So we're going to take a step back to think to how binary white dwarf stars form, so how we get to cataclysmic variable stars. Let's start with looking at the white dwarf in this case. So if you have a slowly rotating white dwarf in a detached binary, meaning there's no accretion flow, that will be the first stage to getting to AR scope. Now, as the angular dynamics of this system evolves and the second star evolves and eventually the two stars come closer together, you will get accretion flow. And that accretion flow will then cause the white dwarf star to start spinning faster. At that stage, it is your typical CV, or your cataclysmic variable star. As white dwarf stars cool, much like copper sulfate crystals that you might have seen in the chemistry lab, they crystallize. So white dwarf stars can crystallize, and while it's crystallizing, the core will then generate a dynamo, similar to a dynamo that we see in a bike book, maybe with a little bit more complicated physics. At this stage, it's something known as an intermediate polar cataclysmic variable system. So these systems have stronger magnetic fields than your typical cataclysmic variable system, and accretion then starts to be suppressed gradually. Eventually, the two systems come close enough together and the white dwarf star is magnetic enough that you get accretion suppressed entirely, and the magnetic fields of the two systems are connected. We say that the system is detached because there's no physical mass transfer occurring within the two systems. This is an intermediate stage, and we believe that this is where we've caught AR SCO. Finally, as the two stars continue to come closer together, their orbital period and their spin period become coalesced, become synchronized. What that means is that they're essentially tidally locked. What we see with the moon, we see the same side of the moon all the time because the moon's spin period and orbital period are synchronized. That's the next stage in the evolution of binaries like this. So stage 5 here, that is then a prepolar, meaning that it's approaching the strongest magnetic stage of being a polar. That's stage 6. So by the time it gets to stage 6, once again, gravitational forces start to take over, which means that you'll start getting matter accreting onto the white dwarf star. But because of its really strong magnetic field, instead of being accreted via an accretion disk, it will be accreted via the magnetic field lines directly onto the poles of the white dwarf star. And stage 6 is where we get to the strongest magnetic CVs. But AR-SCO is just an intermediate stage according to this model. It's possible that it is a very short-lived stage. That's why we see a lot more non-magnetic CVs and magnetic CVs compared to these intermediate white dwarf pulsar type systems. And that brings me to one of the final questions in this presentation, which is, are there other white dwarf pulsars? Okay, I think my screen froze for a minute. Is it still sharing? Fantastic. Yeah. And we do think so. In fact, we have definitely got conclusive evidence for a second white dwarf pulsar, J1912. This was also led by researchers at Warwick. And once again, like AR-SCO, we see a contribution from a blue star, that's a white dwarf, and we see contribution from a red star, which is a red dwarf or an M dwarf. Comparing the properties of AR-SCO and J1912, J1912 has a slightly slower orbital period, so it's 4 hours, and the spin period of the white dwarf is about 5 minutes. But one odd thing about the second white dwarf pulsar J1912 is that there's actually some evidence of accretion. The spectrum shows signs of mass transfer, which is not what we expected from AR-SCO. So it's possible that J1912 actually sits between stage 3 and stage 4. So we've somehow just captured a snapshot of its evolution, we think. And that leads to further questions. So is J1912 doing a similar thing to AR SCO? We need more observations to be able to, longer term observations to be able to confirm this, but also we could benefit from having more systems detected that are white dwarf pulsars. And that brings me to this recent paper that came out last year, that was written by one of my colleagues at Warwick. And that's the third white dwarf pulsar that we have confirmed, once again led by researchers at Warwick. So we seem to have a bit of an interest in white dwarf pulsars. So yeah, this is the third white dwarf pulsar system that was detected. This paper confirms the optical properties of it. So yeah, I have the honor of being a co-author on this paper because I'm currently working on the radio observations of this white dwarf pulsar. And as if you take a look at this paper, then you will see it. Then that we do have preliminary radio observations, and what I found with that is that the third white dwarf pulsar, J2306, also emits in the radio. What I'm currently working on is trying to figure out if it also shows the same pulses that we see in optical in the radio as well. So do keep your eyes peeled on white dwarf pulsars, because they are one of the next big things in white dwarf astronomy. So that brings me to the end of my presentation. We've got a lot of interesting physics to learn from white dwarf pulsars. They do leave us with more questions than answers, and we're actively looking for and investigating this peculiar type of this white dwarf binary. And with that, I'm happy to answer any questions that you may have. Thank you for your attention.
Well, thank you, Anwesha. That was absolutely fascinating. And yet again, it just shows that we are still learning about the universe of which we're part. So thank you so much for sharing that.
I just realized that I forgot to show the last slide, so
Oh, cool.
I'll leave this slide on for
Okay,
the time being. So this is just an astronomy project if you're interested and you can get involved with. One of them is called Kilonova Seekers, and that's a project that's led by some physicists who work in the astronomy group at Warwick, and this uses the GOTO telescopes. So yeah, it's a citizen science project where you can take part in identifying kilonovae. And the other one is SLU, which maybe some people have already heard of, but that's where you can use a network of telescopes to essentially conduct your own observations. So I'll just leave that on there if anyone wants to check that out.
fantastic. Thank you. I'll hand it over to Will to corral the questions from the Zoom chat and from YouTube. So over to you, Will.
Thank you very much. Well, I've definitely learned a lot about all the different types of white dwarfs there. It was excellent. Thank you. So we will go on to first questions from our members on Zoom. And speak now, Francis, if you can. If not, I will read your couple of questions out. So if I don't hear from you, I shall just go ahead and read them. So as Francis is unable to ask, I'll just précis Francis' question, first question. He basically asked that because white dwarfs are end-stage stars, just wants you to confirm how there's protoplanetary disk stuff left with white dwarfs. I wonder if you can just explain that, or whether there was just a misinterpretation from our side there.
Of course, no problem at all. I'm sorry, I think I might have gone through that section a bit fast as well. So protoplanetary disks are the absolute first stage of how we get to a star, and a white dwarf is the end stage. So if I understand the question, then it's asking about how we can get any protoplanetary disk left at the white dwarf stage. Yeah. And the answer is that we don't have any of the protoplanetary disk left at the end the white dwarf stage. So yeah, by the time that it gets to the stage that it's a white dwarf, the protoplanetary disk has already collapsed to form the star that has now evolved to form the white dwarf star. The same applies to protoplanetary disks with binary stars. So you could have two stars within the protoplanetary disks, and the protoplanetary disk will then have collapsed to form two stars. So there will be none of the disk left, and then both the stars evolve. You get one white dwarf and one, say, M dwarf. But yeah, you don't have any of the protoplanetary disk, as you've correctly pointed out there, by the time it gets to the white dwarf stage.
Okay, no, that's great. And Francis's second question is, in a pulsar, why is the spin axis very different from the magnetic axis?
That is a fantastic question, and I will have to admit that this is not my area of expertise. So, yeah, do take what I say with a pinch of salt because it could be wrong. But from what I understand, the spin and the magnetic axes can be quite different because of how energetic the supernova explosion itself is. So that very process might knock off some of the matter within the leftover core of the star, such that the magnetic and the spin axes will no longer be aligned. I'm very hesitant to go into more detail about that, but yeah, hopefully that answers your question a little bit. Apologies.
No, that's great. Marvelous stuff. And Ramsey, if you'd like to unmute and ask your question, please.
Sure, can you hear me?
Yes.
Thank you for a fascinating talk. I wanted to ask you about the revolving binaries. If they're going round each other or rotating about their center of gravity in 5 to 10 minutes, they must be going at quite a velocity. Can you notice that in any Doppler shift, or does one thing cancel out the other?
Absolutely. So that's a great question. And indeed, we can detect the Doppler shift. So this is something known as the radial velocity method. You might have heard of this in the context of exoplanet detection. So in a radial velocity method, what we're looking for is tiny deviations in the spectrum of the system itself. So what we see is that so if you think of two stars that are going around each other, at some point, let's say star A will be coming closer towards us, and then later in its orbital phase, it'll be going further away from us as it's about to go behind star B. So while it's coming towards us, the light will appear to be slightly blue shifted. So shifted towards the bluer end of the spectrum, and while it's going behind it, it'll be shifted to the red end of the spectrum. And indeed, as with exoplanets, we can see this with white dwarf stars as well, except that the spectra look a little bit different. So yeah, we absolutely do see the Doppler effect affecting binaries like white dwarf stars. So wherever you have a binary, you can apply the radial velocity method almost all the time.
Fantastic. Thanks very much for your answer and your talk.
Are there any further questions from our Zoom members before I move to YouTube? Oh, looks like one has just popped in. Jim, if you want to go ahead and unmute and ask.
So I'm just going to connect my laptop to the charger.
That's all right.
Okay, there we go. That should have fixed it. Yeah.
Thanks, Phil. Yeah, thanks for a great talk. Just to follow up to Ramsey's question, with the Doppler shift, does that give you an indication, given that you'll see a Doppler shift in the spectrum of each of the stars, or you don't know which is which, but does that give you an indication of the mass of each one? Because I guess the difference in Doppler shift will indicate a difference in the mass of the two stars orbiting.
Indeed, yeah. So the so changes like that in the spectra will, that does give us a hint as to what the mass dynamics are of the system. In addition to that, we can also use the orbital parameters to figure out how massive the stars are, like looking at how quickly the stars orbit each other and how fast they're spinning, as well. So yeah, the Doppler shift can absolutely tell us a lot about the mass of the system.
Excellent. Nigel, if you'd like to unmute and ask your question.
Yes, thanks very much, Anwesha, for a great
You
talk.
switched the internet off.
I don't know if you can hear me. Can you hear me okay?
Yes,
Yep.
I can.
I thank you for a good talk. That was really interesting. I wondered, since you're actively looking for more white dwarf pulsar systems, are the recent developments like all sky surveys like the Vera Rubin, are they important in looking for these?
That's a great question. So, as far as I know, the Vera Rubin isn't specifically looking for white dwarf pulsars at this stage, but one of the ways that we do use surveys like the Catalina Sky Survey, for instance, that I mentioned, is that there are lots of surveys that obtain spectra for different targets. So one of the search strategies to find white dwarf pulsar candidates is to look at archival spectra of several white dwarf binaries in general. And because we have detailed spectra for AR-SCO, J1912, and now J2306 as well, we can then compare the spectra of these confirmed white dwarf pulsars with these candidate white dwarf binary systems that we have. Wherever we think we have a good match between the white dwarf pulsar that we have confirmed and this potential candidate, we can then use that as we can then use that as an argument in telescope proposals on why we should observe that system because we think it's a white dwarf pulsar. So yeah, it's essentially comparing the templates to the unknown.
Yes. Okay, thank you.
Thank you.
Excellent. We'll move on to YouTube question now. Apologies, so my internet just dropped out before Nigel's question there, so apologies if there was a little bit of confusion briefly. So we have a question from Martin Pride 609. The same or different? If different, will that change the outcome for the white dwarf star?
Would you be able to repeat the first half of that question, please?
Yes, of course. Is the material of the white dwarf and donor star the same or different?
Oh, okay. Yeah, that's an excellent question.
And if yeah, and then if different, will that change the outcome for the white dwarf star type, I presume?
Yeah, so in a white dwarf pulsar, the material or the constituents of both the stars will be quite different. So in a white dwarf star, you're predominantly left with a carbon-oxygen core. Because that's the leftover core from when that star was a red giant star. Whereas in the case of the donor star, the M dwarf, you'll still have large amounts of hydrogen and helium as well. So it'll be predominantly hydrogen with some amount of helium in it as well. But yeah. So essentially, you're having this hot hydrogen/helium material being accreted onto what's already a carbon-oxygen core of a star. Depending on whether it is hydrogen or helium dominated, you might get different types of outbursts, and you will see those differences appearing in the spectrum of the systems as well, because hydrogen and helium will peak at different wavelengths. So yeah, that will affect whether it's hydrogen or helium or some other material being accreted, that will impact the results quite significantly. And another really interesting thing is that sometimes in white dwarf stars, you will get trace signatures of heavy metals or heavier metals, and those that can actually be signs of planetary debris that has accreted onto the white dwarf in some cases. So yeah, the spectra of the binary or of the white dwarf can tell us a lot about the materials around it.
Excellent, excellent. That's great. And we've just had a question from Paul Blackwell at MC6Z. Is the period of the pulses in the dwarf star binary the same as the orbital period?
Right. So in this, in the case of the white dwarf pulsar, when we, this is a bit of a tricky point that I think I might have glossed over it a bit. So apologies for that. So when we talk about the pulses that we see that from the system overall rather than from an individual star as such. So the 5-hour period, for instance, that we have in the second white dwarf pulsar, that is the orbital period of the system. So that's how long it takes for the stars to go around each other. Now it is modular, so we also see signatures like the noise that we saw in the light curve in the case of AR-SCO on the order of a few minutes. So yeah, that we see signatures of that very clearly because it's rotating. The white dwarf is rotating very rapidly. The M dwarf will be rotating much slower than the order of 2 minutes. It will be closer to the orbital period or even larger than the orbital period. And that difference in the spin period of the white dwarf and the M dwarf is what allows the systems to become synchronized in a later stage. So in polars, when they're fully magnetic, you finally have the spin and orbital period of the stars fully synchronized. So yeah, they do start off as different, but they evolve to be closer to each other.
Excellent. Well, thank you very much, Anwesha. That's all questions that we have. So over to
Great.
yourself,
Thank you.
Neil.
Thank you, Will. Thanks for corralling all those questions. Well, Anwesha, it's definitely the case that the quality and interest of the talk is reflected in the number and type of questions. So you've obviously done a very good job of engaging the audience on this Friday evening. So once again, let's thank Anwesha for a fabulous talk.
Thank you very much. It's been a pleasure to talk tonight. Thank you.
And as I said earlier, Anwesha, you're welcome to hang around and hear about what we've got coming up next.
Yeah, I'd love to hear that. Thank you.
Okay, so to close out the evening, let's take a look at what we have coming up in the next few months. We're coming towards the end of our events in April, but as I hinted at a couple of times, we had something happening today. So earlier on today, we had a great presence in East Lothian at Archerfield. We were attending the Wonders of Space event as part of the Science Festival. When I arrived at the venue this morning, our host informed me that they'd sold 600 tickets. So I was hopeful that the clouds would part and the sun would appear so that the audience would have something to look at. And despite my best efforts as president and getting some audience participation to try and blow, we didn't succeed in moving the clouds until about 3:45. And when that happened, we were inundated. So we'd spent most of the day talking about the theory. Never mind about looking for binary stars. We were struggling just to find one. and eventually it made an appearance, and so it was great to finish the day on a high note. So for the rest of this month, we've got one more event, and that is our telescope help shop in Corstorphine. That's a week tomorrow. More details of that will appear in the newsletter. If you do want to come along, then please do fill in the registration, and we'll see you in Corstorphine a week on Saturday. So that's April. Moving into May, our main meeting is on Friday the 1st, and our guest speaker is Professor Ian Robson, a decorated professional astronomer who's very active in outreach and a keen presenter on astronomy topics. And Ian summarises his talk as follows. Since the first use of telescopes in 1609, astronomers have made amazing discoveries about the universe in which we live, and we've heard tonight that those discoveries are still being made to this day. Technological improvements have meant bigger and better telescopes and novel instruments spanning the entire electromagnetic spectrum and beyond are being developed. And this talk gives an illustrated overview of the development and the discoveries that have led to our current knowledge of the universe, and concludes with the onset of big data in modern astronomy and the changing scene facing astronomers today. And again, we've heard something of the challenges that these things present from Anwesha this evening. Our mid-month online meeting, our guest speaker is Dr. Krisa Avalidou, who is a lecturer in planetary science at the University of Leicester. Krisa was a fellow at the European Space Agency, where she worked on ground-based observations of meteoroid impacts on the Moon, and she's developed methods to derive the mass and size of small impactors. She then moved to Nice Observatory, where she worked on asteroid science, and she's been a collaborator on the NASA OSIRIS-REx space mission to the asteroid Bennu. In Chris's talk, entitled Meteorite Impacts on the Moon, she will describe how, for more than 25 years, the lunar surface has been monitored with small telescopes, detecting collisions by recording the produced light. And the initial purpose of this was to understand the flux of these events and the estimation of flux in near-Earth objects. And this is important for things that might affect us as a civilization, with events such as the Chelyabinsk one in 2013, a good example of how close things can come. In members and other events, on Wednesday the 6th, we have our monthly imaging and observing group. That's an online session for members only. And finally, looking ahead to June, which is our final month before the summer break. I can't believe I'm saying that, but it's true. Our main meeting and also our AGM is on Friday the 5th of June. And our guest speaker that evening is Dr. Will Chung, a well-known astronomer, astrophotographer, and astronomy communicator based in the UK. Recognised for his work with the Northumberland Dark Sky Park. He's a prominent figure in aurora chasing and education, and he's been recognised as a Fellow of the Royal Astronomical Society. And the working title of Will's talk is Chasing and Photographing the Aurora. So more details on that will be published nearer the time, as will more details about the AGM. Our mid-month meeting, online meeting, our guest speaker is Paul Fellows, another highly decorated and distinguished scientist and astronomer. That includes the award of the British Empire Medal in the 2025 New Year's Honours List. The usual story told of the end stage of giant stars is that they either finish up as a neutron star or collapse to a black hole. And again, there's been connections to Anwesha's talk this evening there. However, in this talk, Paul looks at other possibilities for exotic forms of matter which may add to the picture, and how the latest observations seem to back up some of these ideas. So that'll be a good way to end our speaking season. Finally, our June imaging and observing meeting is on Wednesday the 10th. Information about most of these events will be available on the events calendar page of the website as soon as it becomes available. We'll also mention them in the newsletters to make sure that you don't forget. And that brings us to the end of this evening's agenda. So once again, Anwesha, thank you very much for joining this evening. I hope everyone enjoyed the talk and look forward to seeing all at future events. So for now, it's a very good night from me, and I will try and provide you with some clear skies for observing very soon. Thank you very much.